Can you see my screen?
Yes.
Yes.
Okay, thank you. First, thank Salting for the nice introduction. I should say I also learned a lot from the discussion with Salting during the first year in Professor lab at MIT. And also thank all the organizers' efforts to make this happen. I think it's a very good platform for the students and young researchers. Today, I will talk about our recent study about wrinkling patterns. And as you can see from the top few image, so we are interested in the patterns of wrinkling on different geometry and with the uniform curvature or curvature gradient. And so I will start the motivation. At first, you can see the first image, that's the embryo development process in the crocodile and the lizard. And you can see that for the early stage, the embryo is kind of a curved cylinder. And when the embryo grow, you can see that so the embryo will become bigger, and also at the skin, you will see some wrinkled deformation. But people now is still arguing it's whether it's a wrinkle or other biological or chemical factors induce this pattern formation. But one thing you can see that this is the structure, you have very complicated geometry and you have non-uniform curvature. And also when you grow your global deformation, you also see this global deformation. And another study is a chicken. And basically chicken and the crocodile, they are similar. And they have this, so chicken will grow feather and crocodile and will grow scale. And you can see that the bottom image is that from the day 6 and there's no pattern. And from the day 7.5, you can see the pattern. And it's like this I cite from the paper. That's the hexagonal. So you can see that a new row add the progressively in the parallel to the existing to a wave of feather formation. And this is a kind of a spreading wave. And if you look carefully, this sort of hexagonal pattern. And when the date so the date 8.5, you can see that the pattern grow wider, and other location you also see the patterns. And this is a very interesting phenomena, and people in different fields try to use a different method or model to understand this. And one model in the biology is the tooling or reaction diffusion systems that rely on the pattern gene expression as an intermediate stage in the pattern formation. Basically, you can form a coupled diffusion equation, and the gene expression and will cause the chemical concentration change. Then you will see some pattern. This is one explanation. And recently there is one paper in Science by Shire, and they also use chicken as a model. And you can see that they also observe the pattern. So that's kind of universal. And also they did a more mechanical analysis that we know that in general for the skin, you can think skin is a multi-layer structure. And you have this epidermis. That's the layer in the outer surface. And then you have dermis, and also you have substrate. So what they did is they first intentionally remove the epidermis. Then you can see that the surface, that's the dermis and the substrate, and you can see this morphology. And they also did that they remove the intermediate layer, that the dermis, on the figure G, you can see that the outer layer, the epidermis, buckled up. That means that the outer layer, the epidermis, is under compression. And this is a very like classical buckling or wrinkling in the like multi-layer like solids. But I wanted to mention that in the tissue, it's really very complicated. You do not only have this mechanical compression, you will also have like active traction due to cell and other chemical, biological like interactions. So it's a very complicated process, but this gives some indication or evidence that the mechanics can play an important role. And this is one example, and I want to share you another example that people found this in the plant. And when you have this hierarchical channel on the right figure, and you can significantly increase the water transport speed. And they did, so they first inspire the authors, Chen and their collaborators, they first get inspiration from nature, this hierarchical microchannel. Then they fabricate with other like methods. Then they do experiments to verify this idea. And for me, I'm interested in the kind of question is how do these hierarchical channel form, and are they wrinkles? And we know that if you have a plant, you have a plant cell wall, and also you have a core, so you can see that there's a hollow structure, and so we may be able to model this as a core shell structure with the outer layer, the shell is grow faster, then you may see wrinkle, and this geometry may give you some like additional factors to form hierarchical microchannel. These are the two examples I found from nature, biological structure, and then I wanted to highlight the scientific questions I wanted to study. I think the purpose of my talk, today's talk, is I hope I can convince you that these are interesting questions. As we know that later I will also show that wrinkles and instability has been studied in the mechanics community for a long time, even for the only for the wrinkling, and maybe it has 20 years. So I wanted to show that we can still find something new and interesting, and then we may be able to connect this understanding with the biological structure and also further for the bio-inspired design. So the question I wanted to answer, actually I don't have an answer yet, but the question I wanted to start is how wrinkles will be distributed on the curved surface. Like the embryo, we can think it's a banded like a cylinder, or later I will show that we can use a torus to mimic this geometry. And for the plant, that is a kind of a cone structure. So for these two geometrical structures, we do not only have a non-zero curvature, we also have a curvature gradient. And then we will discuss how the curvature and the curvature gradient will influence the pattern distribution, wrinkling patterns. I will show some like results that we develop a mechanical model that we wanted to study the competition between this geometry incompatibility and uniformly energy preferred wrinkle. We know that if we treat these patterns as a wrinkle, and the wrinkle actually is formed due to the energy minimization. But when you have a curvature gradient and you move your wrinkle from one location to another location, you will see this geometry incompatibility. Then I want to highlight that the wrinkling pattern is determined by the competition between these two factors. these are the questions I wanted to discuss. And next, I will give a very quick literature review that people, as I mentioned, that people have been studying the wrinkles for a long time. That's for the 10 years ago, and people use the PDMS system. You can form very complex 2D patterns. And also, in the last few years, people are also interested in the patterns in the curved space, like Professor Pedro Reit's group and Professor Crosby's group. They did this sphere, and there are more other studies, and so these are very like classical studies in the field. So I discuss very briefly. If you are interested, you can read the papers in my reference. And now you can see that many people are also interested in the wrinkles on the curved space. And at the bottom two, I choose two examples that all the previous examples I discussed are based on the thin film on solid substrate. And now we want to, the bottom is the thin film on the liquid substrate. You can also see very complex patterns. And that's the little review. Now I wanted to introduce the problem setup. I said that we first wanted to understand the embryo development, like the pattern formation. So the shape like it's similar to a torus that we choose to simulate a torus wrinkle. For a torus, you have two directions, this blue and this red direction. And for the model, we have a tri-layer new hooking model. And for the material property, we use a simple model is a new hooking material. And for the driving force to form the wrinkle, we let the outer layer, this dark blue, has an expansion. And in general, the dark layer, the modulus is larger than the light blue. And we call that is the intermediate layer. We also have a core, the red core, that you can tune the stiffness. And so that's the model, and I will show that like as I mentioned that the real embryo is very complicated. We just want to use a mechanical model to see whether we can get some understanding. And this paper has been published in Source Matter. First, I will show you two videos. These two videos, and only different parameter is the modulus of the core, the intermediate layer and the core. The mu2 is the, sorry. So the mu2 is the modulus of the red core. Mu1 is the modulus of light blue. You can see that when the core is soft, and you see the sinusoidal wrinkle. And also you can observe the global deformation of the torus. And when the core is red, so when the core is very rigid, you see hexagonal pattern, and you didn't see the global change. And then you can think that the red core can serve a constraint of global deformation. And we also run a wider range of parameters that the vertical axis, that's mu2 over mu1, that from 120 and 100. The top figures show that the core is soft. You will have significant global deformation. The bottom is the top. The core is stiff. You do not have global deformation. And you can see that we have a very rich phenomena. And here I want to highlight the bottom, that you can see when your core is very stiff, you see the hexagonal pattern emerge at the outer surface, then propagate into the inner surface. And I will highlight these results in the next few slides. And we made a phase diagram that we have this the factor mu2 and over mu1 that control the global deformation. And for the expansion, that's the initial buckling and the post buckling. So we can have a very complete phase diagram. And we also do the mechanical analysis, the stress analysis, to understand why we can have different patterns when we only change one parameter, only change the ratio C2 over C1, mu2 over mu1. You can see that the two extreme cases, the blue curve on the figure A, that is mu2 over mu1 is 1000. That means the core is very stiff. And you can see that the maximum stress is in the at the outer surface. That's the phi equal to 0. And also sigma theta theta, sigma phi phi, they are very close. The ratio is close to 1. Then that they are close to equal biaxial compression. Then you will have a hexagonal pattern. And also you can notice that the maximum stress is at the outer surface. That's why you have the hexagonal pattern emerge at the outer surface first. And if you see the bottom, the green curve, and when your core is very soft, mu2 over mu1 is only 0.01. And now you see a reversed case that your sigma theta theta, so that's the long axial direction, and it's much smaller than the circumferential direction, the sigma phi phi. And the ratio can be as large as 1.4. And then you can see that this is far away from equal biaxial compression, and that's why you observe the sinusoidal wrinkles. And you also notice that now the maximum force stress appear at the inner surface. Then you will see that the sinusoidal wrinkle will first appear at the inner surface, then propagate to the outer surface. This shows that the importance of the global deformation and also non-uniform curvature will influence the patterns. And this are already in our paper, so if you are interested, you can read the paper. And I wanted to highlight this slide that I mentioned the propagation. And also in the first slide, I said that in the biology, in the chicken embryo, people observe the spreading of pattern. In our mechanical system, we can also see similar behavior. When the expansion is small, you can see the hexagonal pattern is start at the outer surface and is only a narrow band. When we further increase the strain, this band width will increase. The pattern propagate from the outer surface to the inner surface. And at a certain value, the pattern will cover all the torus. And then we can kind of compare these results with the experiments of the chicken embryo pattern. You can see that initially the pattern start from the outer surface. This also kind of agree with the chicken embryo. And then you can see the propagation. And this is like our simple mechanical model provide can create this phenomena, but we need more study to quantify the contribution from mechanics, biology, and chemistry. And the next few slides, I wanted to slightly change the topic. I use this like a corn, like a plant as a motivation, but we don't have the results yet. And interestingly, we are also working on another problem, and it's the water droplet on thin film. And once you put a water droplet on thin film, you will observe wrinkles due to the surface tension difference. You can simplify this into a Lamé problem, and people in particularly in the UMass has been working on this a lot. And recently we collaborated with Benny from UMass and Joy Paulson at the SU Physics. We studied this mesoscale structure of wrinkle patterns. And previously, the science paper in Huang and the collaborator developed is they put a water droplet on the thin film, but the thin film is relatively small, and the water droplet is also small. And in our experiments, we do two in the lower parts. You can see that for the radius, the first one, the panel A, the radius is 6 millimeter. Panel B, the radius is 30 millimeter. So we change the size of the thin film and also change the radius of the water droplet. We can observe two different regimes. For the regime 1, we call the defect-free, that you have only radial wrinkles. And so your wrinkle number when you change at a different location is a constant. In the second regime, that you can see the new wrinkle keep coming up. And when you count the wrinkle number as a function of radial direction, you will see a linear increase as so as you move from inner surface to the outer surface. And panel C and D are the simulations. And we can reproduce this phenomena. The panel I is a phase diagram. And we did a lot of study and to find the two phase. The dashed line is a theoretical boundary from the energy analysis. Now we have this two regime. We want to understand what's the difference and what's the governing factors for these two regimes. So this is the bifurcated wrinkles. The first case that we know that for this system is a thin film on the liquid substrate. And we know there are competing, so first the competing energy is the compression and the gravity. And so the compression will be released by bending. So it's governed by bending stiffness and the gravity force. We will have this wavelength. But if we want to keep this wrinkle number constant, when you move away from the inner surface, and your wavelength actually will become larger. So then you will increase the energy of your system. And this is one factor of the energy source. And the second source is you can choose that, say that the wavelength is too large, it's not an energy minimum state. And then you need to change your wrinkle wave number. When you change your wave number, it's kind of, you should to have more wrinkle form. And then it's kind of like defects in liquid crystal crystal. Like you insert one layer of material in the crystal, that can be a dislocation. And in the liquid crystal that you tune your preferred direction that can be connected to the twist grain boundary in the liquid crystal. And this kind of defect mode will increase energy. And then the competition between these two energy terms will give us a mesoscale L parallel. And our collaborator Benny did a multi-scale perturbation analysis, and he derived an equation for the mesoscale length scale. And I trust Benny, and so we just directly use these equations and to compare the equation with the simulation and experiments. And also, to be honest, the analysis is very complicated. I cannot fully follow, but I think Benny is an expert in this field. So we are confident about these equations. And here is a detailed behavior of this bifurcated wrinkle. You can see that's one typical like simulation. This so the color, that means your wrinkle amplitude. The dark color, that means your amplitude is larger. The light color, that means your amplitude is smaller. And we can use this function. C is a two-wave superposition, and then based on the wrinkle amplitude function as a function of theta, we can do the Fourier theory. So we can get a two-wave peak. From this two-wave peak, we can define what's L parallel. We can also, visually, you can see that here we have one bifurcation and we have another bifurcation. Then we can measure the distance between the two bifurcations. And after we have this analysis tools, we compare the theoretical prediction with experiments and simulation, and we can get the like agreement in at least in the trend that when you move away from the inner surface to the outer surface, you can see L parallel increase that both in the experiments and in the simulation. And we did various simulation and the experiments and the general trend are consistent with the theory. So next, I want this my summary slides that I show you two examples. One is the embryo, the pattern. You can see that, and that's from the experimental image on the right. That's a fossil pattern. We can kind of identify hexagonal, heptagon, and pentagon patterns. And on the right is the torus pattern. We will also see the hexagonal and the heptagon and the pentagon patterns. So I think there are some connection between these two systems, but we need to do more to really understand like what's the contribution, how much mechanics can play a role. Similarly, for the annular wrinkle and the hierarchical microchannels, as I mentioned that these two seem like to disconnect like a problem. But if we look carefully about the wrinkle bifurcation, and we can find that they can be connected, that you have wrinkle on the microchannel, and then you have new wrinkle form, and that's bifurcated to from one wrinkle to two. So similarly to the annular wrinkle. And that's like I mentioned that in this talk, I don't want to close the question. I wanted to pose the question to a more general audience that we see some preliminary results. It's very interesting for the patterns on curved space, but we need to have more studies that we need a collaboration from different fields with biology, with plant science, and with like physics and other fields. And I will, this reference, that's the acknowledgement. I think I will stop here. And so I will be happy to answer any questions.
Thanks, it's a very impressive talk. We have a few minutes. You can still actually share your screen. And I basically, other people may ask you a few questions. Let's give 2 to 3 minutes for a few more questions. Bianca. Since you have a question, go ahead.
Yes, thank you very much. Thank you. The talk was really very interesting. I have a question on slide 14. If you can please go back to that. Oh no, 14. One, yes, exactly. So in this picture, maybe you said and I missed it. I don't understand what the colors are, like the blue and the red mean.
Oh, sorry, I think I didn't mention that. So you can see that the red are pentagon, and the red are heptagon, and the blue are pentagon. So, and this like other black are hexagon.
Okay, okay. I thought that the other was were similar to the red in some sense.
So we first identify each node like this red dots, then we like this is a circular dots, then we use the Voronoi to construct this polygon. Then we count it's a heptagon, pentagon, and the hexagon.
Do you think that the number of hexagons and pentagons is pretty much comparable in this case? Or there is a prevalence
of? Yeah, that's a very good question. That first we know that and we already counted like for the last one, the number of heptagon and pentagon, they are the same. Because if you think like people studying physics about the charge distributed on curved surface, this so this like torus has the neutral like a charge. So if you count the heptagon and the pentagon, they should be the same. But like how to understand this distribution, and we are not sure yet. And we see some trend like the distribution of dislocation if you think a pair of the heptagon and pentagon. But for the pattern, we do not fully understand it yet.
Thank you.
Thank you.
Hi, Professor Ye Fei.
Hey, Teng, a very nice talk. So The more frequent I listen to your talk, the more I learned. So can you go back to page 11? So I have a general question, or maybe 12. Okay. So my general question is, so you have a very nice phase diagram. So you're predicting the equilibrium. But let's imagine I have, let's consider the Euler buckling. That's the classic textbook knowledge. So in Euler buckling, we have many frequencies that are metastable. When you really have a buckling, you just choose one, maybe the longest wavelength one. But if the surrounding, let's say, is a viscous fluid, or you may choose other frequency. So I wonder whether in your wrinkling you have a similar behavior. You may have many possible metastable states, but somehow, depending on certain kinetics, maybe you have it, maybe you don't have it, then you would choose a rather different metastable state than what you predict from your phase diagram. Or even worse, can you go back to 11, page 11?
Yeah.
So let's say even worse, when you see some kind of wrinkling or buckling or whatever on this one, maybe you see a sudden, a localized kink, maybe a localized wrinkling that is large enough that fails the entire thing before you see the more uniform wrinkling elsewhere. Is that possible? Either that's energetically possible or kinetically possible.
So that's a very good question. And first, I think the simulation is kind of different from experiments. For the experiment, you have a lot of noise and like imperfection. Then you may have more chance to have localization. In the simulation, it's kind of a cleaner system. And I think in general, this phase should be there. And but like one thing I totally agree, metastable, you can see this hexagonal pattern. And so you may have infinity combination of hexagonal pattern. And so maybe I can go to slides like 14. You can see that my current understanding that, so like Bianca's question, it's where you have a hexagonal and a heptagon, pentagon, I don't know. That's like fully maybe determined by your numerical noise or other random perturbation. But I think this like overall statistical distribution of this pentagon, heptagon, that should be stable. And I should also mention that we intentionally choose this system that you have, so we have a tri-layer. So for the tri-layer, we intentionally choose the outer layer, mu0 over mu1 is 10. Because we did a lot of simulations that for this kind of modular ratio, the hexagonal pattern is stable. But many people use experiments like in the metal on the PDMS. That ratio is 1000. People already know that you kind of have a chaotic system. So for that is like many things that can happen. You cannot have a very like a clean phase diagram. So I totally agree with you that it depends a lot of parameters. So even the problem is simple, but we have like a geometry, material parameters. So a lot of combination. We only report a subset of phase diagram, I think.
Very nice work. Yeah.
Thank you.
Yeah, okay. Thank you, Professor Teng Zhang, for your impressive talk.